Hello and welcome to session one of the product value selling training series. My name is Brian Burkhart and I am the product line manager for the consolidated pilot valves. And for this session, I'll be walking you through about a 30-minute presentation on the consolidated 2900 pilot valve and a case study where you can actually upgrade or replace API 526 direct spring valves with the pilot valve and the benefits associated for the customer with this application. And so with that, I'm going to go ahead and get started. But before we go straight to the case study, I'd like to start you off with just a little bit of background and put this into context, how the pilot valve and specifically the 2900 sort of fits into the application. And so if we look at the National Board, who's the governing body for pressure relief devices that are protecting systems from overpressure events, they define a pressure relief device, or a PRD, as a device that provides a means of venting excess pressure, which could rupture a boiler or pressure vessel. A pressure relief device is the last line of defense for safety. If all other safety devices or operating controls fail, the pressure relief device must be capable of venting excess pressure. So essentially, when there's this unexpected rise in pressure beyond what's safe for the boiler or the vessel, the pressure relief device is intended to open and relieve that pressure and protect life, property, and equipment that it's protecting. Now, there's lots of different types of pressure relief devices, and so if we put ourselves in the shoes of a customer, what are they looking for in a pressure relief device? Or more specifically, if there were a perfect pressure relief device, what exactly would that look like? What would its attributes be? And so what we do is we really break this down into three different phases. So the first phase is before the relief event happens. And this is the phase in which most pressure relief devices are spending the majority of their time. And so at this phase, the pressure is at a normal level, and we want that device to be closed. If it were to be open when it's not needed, it would be flowing capacity and wasting process for a customer. Sure, it would be protecting their system, but it would have this sort of this side effect of wasting process and therefore costing money to the customer. Secondly, not only do we want it to be closed, but we want it to not be leaking. And ideally, we want it to have zero leakage, all the way up to 100% of set pressure. And set pressure is the pressure at which the device is intended to open and relieve the pressure. Typically, the relief devices are set somewhere around the MAWP, which is the maximum allowable working pressure of the boiler or the vessel that they are protecting. So we'd like to have zero leakage so that the customer isn't losing that unwanted process through the relief device. Secondly, the device is intended to open and protect the system whenever that overpressure event occurs. And so when that happens during the relief event, let's say, we want our device to open and open exactly when it's supposed to, right? So if the relief device doesn't open, then it's not protecting the system. And now if it opens early or too low of a pressure, we are wasting process. Maybe we're having some leakage, or maybe it just opens too soon and it didn't actually need to open to protect the system. And we waste some process there, cost the customer money. Now, we also don't want it opening too late, or the overpressure could be so much that it could damage the valve or the system. And so we want it to open exactly when it reaches set pressure. Secondly, not only do we want it to open when it's supposed to, but we want it to flow how much it's supposed to. And so the relief that we define that in terms of capacity. And so we want it to relieve enough capacity to protect the system, but not more than is required to protect the system, because again, that would be wasted process for the customer. And if the device did not flow enough capacity to protect the system, then of course the overpressure would overcome the device's relief capacity, and it could still cause damage to the system. And then finally, we want it to open when it's supposed to. We want it to flow how much it's supposed to, but we also want it to do it in a stable manner. We say without chatter or flutter. And so if the valve opens and relieves the capacity, but it's entering into a rapid cycling, which we call chatter, the valve could be damaging the seat area, which would potentially cause it to leak once it closes back down. It could damage internal components, which would require the customer to send their valve in for service and replace parts prematurely. And this chatter can even be so catastrophic and violent that it can damage the piping and the equipment around the valve. So it's certainly important that the valve opens and flows in a stable manner. And then finally, once the system pressure normalizes and comes back down, we want that device to reclose on its own. So we don't want, in a perfect world, we don't want to have to manually close that device or have to replace that device in order for it to reclose, or go up to it and have to like hit it with a hammer or something like this to get it to close back down. We want it to close back down all by itself after the relief event. And we want the time between the point where it's reached its full rated capacity and the time when it closes back down. We want that time to be as minimal as possible. We call this minimum blowdown. Because if it takes too long to close, again, it's relieving more capacity than it needs to, and this can be wasteful. And then finally, we want it to return back to its original state before the relief event with our zero leakage. So we want it to be closed and back to zero leakage. And this is kind of a circular cycle that we want to see the device doing. And so when it comes to pressure relief devices, the customer has many different options, and some options are better for particular applications. There's kind of commercial effects to this too in terms of pricing and lead time and all that great stuff. But if we look from a pure technical standpoint at the function of these different devices, and we weigh that against the three criteria that we outlined before, this table shows you 4 of the most common pressure relief devices and how they line up to those 3 criteria. And so we start with the rupture disc. The rupture disc is essentially a non-reclosing piece of metal that's designed to burst at a particular set pressure. And so before it opens, the relief device, the rupture disc is great. So there's zero leakage across a rupture disc, and certainly it's closed, so we give it a plus. However, during a relief event, that rupture disc is going to burst open, and it's going to continue to flow until you've isolated the rupture disc. And so what this means is you can have unwanted process loss. It's going to continue to flow. It's going to flow more capacity than it needs, and it can be a costly event for the customer. And then finally, it's not going to reclose on its own, and it's not going to return, obviously, back to zero leakage. So we've got minuses in those categories. Second, we look at a weight-loaded valve. So a weight-loaded is exactly how it sounds. You've got a pallet of weights stacked against an inlet pressure. These are very popular on tanks or storage tanks, and sometimes we call them breather vents. What they're really intended to do is throughout the day, they're going to breathe in and out as the sun comes up, heats up the tank, and then the sun goes back down and cools down the tank. The weight-loaded relief device will allow that tank to breathe in and out so that it doesn't have an overpressure situation or a vacuum. It doesn't pull a vacuum and kind of suck itself in. And so typically they're going to blanket these tanks with an inert gas because you can see here we've got a minus. Beforehand, you get very, very poor seat tightness on a weight-loaded product. And so that's why we've got minuses before and after, is because the pressure acts up against those weights, and those weights are not very, they're not heavy enough to cause high seat tightness, right? So that's weight-loaded technology. Then we move on to the spring-loaded pressure relief valve, and this is one that we're probably the most familiar with. And it's similar to the weight-loaded, except instead of a weight, you've got a spring acting down on the inlet pressure. And this allows us to get quite a bit better of a seat. And so on a spring-loaded relief valve with a metal seat in a Section 8 application, we're typically going to see about a 90% operating pressure, where we'll start to see some bubbles per minute leakage across that seat. And that's defined by a standard called API 527, which allows a certain number of bubbles per minute on at 90% of set pressure on a metal seated spring valve. We can get that operating pressure up to maybe 93% with a soft seat. The maxi flows can get up to 94, 95 on steam service and Section 1 applications. But generally speaking, you're going to be right there in the low 90s in terms of operating pressure before you start to see seat leakage on a spring valve. And so for that reason, we've got sort of an average or a medium rating for the before phase. Now during, most spring valves, especially on gas, are going to pop open, so they have a pop action. And what this means is when they hit their set pressure, they're going to go into full lift, pop right into full lift, and it's going to flow the full rated capacity of the valve, which oftentimes, I would say the majority of the time, is more than the required capacity that the system needs to be protected. There's exceptions, like for example, if you're using a restricted lift or something like that, but generally speaking, this valve is going to flow more capacity than is required to protect the system. Can also lead to things like valve chatter and give us some instability too. So for that reason as well, we're giving it a medium rating for during. And then after, it's going to turn right back to the before scenario that you saw before. So definitely a versatile valve that's good for many applications. But there are a few applications, and we're going to talk about these more in depth here and in the case study, where a pilot valve can be very beneficial to a customer's application. And so a few of those, let's just look at the before state. So a pilot valve, we talked about wanting zero leakage up to 100% of set pressure. A pilot valve is the only pressure relief device that will allow us to get all the way up to 98% of set pressure with having zero leakage across the seat. And so that one will get us all the way up to 98% with zero leakage. And that is very efficient for the customer. So for that, we have a plus. Secondly, during a relief event, a pilot valve can have a modulating action instead of just a pop action. And what this means is that the valve will open proportional to the inlet pressure and the required capacity. And so it will flow only the required capacity, and it won't go directly into full lift and flow the full rated capacity. So this gives the customer some efficiency gains and will give them some savings in real dollars. Secondly, this can also if you got an application where your spring valve may be chattering due to inlet line loss or the valve being oversized for the application, a pilot valve can resolve that too with the modulating action as well as the remote sense option. So if we consider those two enhancements of a pilot valve, we give it a plus in the during phase as well, during that overpressure event. And then finally, the pilot valve will reclose on its own and return back to the 98% seat tightness that we started at before. So in summary, different valves are good for different applications, right? And I wouldn't say to put a pilot valve in every application, but in those applications where you have high inlet line loss, potentially an oversized valve, or maybe you need to operate higher than 90% of set pressure without getting that seat leakage, and some various other ones that we may touch on as well. A pilot valve is a great fit there. And really our motto here is let's put the right pressure relief device in the right application and make sure our customers are aware. And our job is to help educate them on that topic. Okay, so we made a lot of claims about the pilot valve and especially along the lines of seat tightness, some of which may be counterintuitive. So let's just take a quick look at how the pilot valve actually achieves this and how it works. And so really we put it into three steps, and they kind of go in a circular motion as needed by the process conditions. And so where the valve is spending the majority of its time is right here with the main valve closed, and this is what we call the normal operating condition. And so here we have an inlet pressure, that's this pink fluid here, and that is acting upward on this disc or this piston right here in the center of the main valve. Now that same pressure is being fed through the inlet sensing tube, and it's loading through the pilot. We call this the pilot valve, and that loads into what we call the main valve dome here on top of that disc or that piston. Now the pressure pushing up is exactly the same as the pressure pushing down. However, the surface area on top of the piston is around 30% larger than the surface area beneath the piston. And so what this means is pressure pushing up, pressure pushing down, but a larger area means the force pushing down will be greater than the force pushing up. And actually what it means is as the pressure increases, the seating force will actually get tighter and tighter. And so it works exactly inversely proportional to the spring valve, which I'll show you in just a moment. Now, when it's time for the pilot to open and that pilot hits set pressure, that pressure in the pilot will act upward on the spring will contract, and the pressure that's in the dome will be relieved through an exhaust vent here in the pilot. That exhaust vent will relieve just a tiny amount of pressure, just enough of what's inside the dome. We can also pipe this process into the main valve here if we don't want to be releasing it to the atmosphere. We have other options where we can pipe it away to a safe location as well if we can't pipe it into the main valve for one reason or another. But anyway, so the after the spring contracts and the pressure from the dome relieves, we see the main valve open. And depending on whether you have a modulating pilot or a pop-acting pilot, that will dictate how the piston acts inside the main valve. But the pressure and the force underneath the piston will be enough to raise the piston and flow the valve. And then once that pressure comes back down, the spring will contract back down, and the pressure will reload back into the dome, and the main valve will shut again, returning to the 98% of seat tightness. And so just to demonstrate the seating force at the seating area, there's two charts here that have on the x-axis system pressure, and then on the y-axis they have the seating force. And so in a direct spring valve, you have the spring pushing down and you have the pressure pushing up. And so what this means is as the system pressure increases, the seating force inside the direct spring valve will actually decrease proportionally until you hit a point at 90% on a metal seated valve where you will begin to see seat leakage across that seat. And it starts very small, but as you increase from 90% up to set pressure, that leakage would rise more and more. You'll begin to see some simmering, and then eventually at 100% of set pressure, the valve will pop open, relieve the pressure. Now on a pilot valve, like we just talked about, it acts inversely proportional to what you see above, where as the system pressure increases, the seating force also increases because that area on the dome is larger, and so that causes the seating force to increase as we increase the pressure. This takes us all the way up to 98% of set pressure, at which point we will begin to see seat leakage across the main valve seat of the pilot valve. And so this is really kind of from a technical perspective how we achieve the greater seat tightness and get those benefits to the customer. All right, so this brings us finally to our case study. And here our case study is, as you could kind of tell, basically what are those applications where a direct spring valve may have been spec'd in and installed where a pilot valve could have been a better option for the customer, right? And so we're talking about high inlet line losses that may be causing valve chatter. Maybe they've got operating pressures at or above 90% of set pressure. Maybe their valve is oversized and it's causing valve chatter. Lots of different scenarios that we've discussed in this presentation so far. Now, every manufacturer of a pressure relief valve, they all have pilot valves. They all generally can provide the same benefits that I outlined to you before, right? We can get greater seat tightness, we can eliminate valve chatter, we can have a modulating valve to just flow the required capacity. pretty much everybody can provide that. Now, we do have some technical advantages. We've got the best seat tightness in the industry at 98% and some things like that. But at that point, you're kind of getting into semantics and splitting hairs. So what is it that we have that nobody else can provide the customer to solve their challenge? And that is in the consolidated 2900 series pilot valve, we have a valve that matches the center to face dimensions of the API 526 direct spring valves and gives all the benefits that we discussed with a pilot. So it's a pilot with the pilot benefits without the extra cost and hassle of having to do piping modification when you do an upgrade or a replacement. And so really there's two ways that we can go about this for the customer to solve their problem. Option number one is if you come across a consolidated 1900 API 526 valve that's installed in one of these applications that maybe you're servicing the valve too much because it's going into rapid cycling. Maybe you're replacing the nozzle and the disc a lot because we're getting damaged seats from rapid cycling or chattering. Maybe there is a need to have higher operating pressures and get rid of that seat leakage across a seat. Whatever the case may be, we can take the consolidated 1900 and upgrade it to a 2900 without having to replace the entire valve. And so what we do is we take the bonnet and the cap and the upper internals off of the 1900, but we preserve the body and the nozzle and the lower internals. And then we put a main valve, we put a 2900 conversion kit with the cover plate and a few other pieces. We marry that up with a pilot, and we have now converted a consolidated 1900 to a 2900. And in many cases, we can do this for around 15 to 20% cheaper than replacing that 1900 with a brand new 1900. And so there's some benefits to the customer there to do an upgrade instead of a replace. Now, if we have a competitor API 526 valve, API 526 is a global standard that primarily for customers that globally standardizes all manufacturers, among other things, on two important things to the customer. Number one is the orifice size, which will correlate to how much the valve will flow in terms of capacity. And number two is the center to face dimensions of the inlet flange and the outlet flange. And so what this means is that everybody's API 526 valve in the world, and here I'm showing you just 4 of some of the major ones, but there's many more, right? The Ferris 2600, the Crosby J series, the JOS, the JLT, all of those, and the Lacer 526 valve. You can take out any of these valves and put in any competitor and the center to face dimensions will line up. However, every competitor's pilot valve has different center to face dimensions than a direct spring valve. So if you were to take out a Crosby J series and put in a competitor pilot valve, or even our own 3900, those center to face dimensions would not line up, and it would require the customer to do piping modification, which is obviously a barrier to them to be able to get those benefits we talked about. And so the consolidated 2900 can replace like for like any of these competitor API 526 valves, and the customer doesn't have to do any piping modifications. And just to highlight, Consolidated is the only manufacturer in the entire world that has a pilot valve where the complete line matches those center to face dimensions. So huge advantage we have here that we can bring to the customer. Now, most important on the entire slide is what is this going to mean to the customer in terms of dollars and cents? This is where it gets down to the investment. Is it worth it for them? And so what we've got down here is some quantified savings that they can enjoy. And so the first one is going to be a one-time installation savings. And what this comes down to is the fact that they don't have to do the piping modification with the 2900, and they would have to with the competitor valves. So when they're comparing our valve to a competitor solution, make sure they understand that they're going to have this upfront investment on the others where they wouldn't have to spend that on ours. And this can be significant. Here we've got between $5,000 and $15,000. This is per installation, and this is a one-time upfront installation savings. So big savings for them there by using the 2900. Secondly, they get an operational savings, which is an ongoing savings, and we quantify this one on a per release basis. And so, for example, if you install a modulating pilot valve instead of a pop-acting direct spring valve, the valve will only flow the required capacity. The pilot valve will only flow the required capacity, and this can mean huge savings to a customer, depending on what that process is, how much it costs, and how long the valve opens. We estimate it to be around $50,000 per release. Now, this is going to vary greatly, again, based on what process we're talking about, how expensive it is, and how long the overpressure event lasts. But $50,000 per release is kind of a safe number to throw out there. And then finally, in terms of size and weight, the pilot valve can offer some size and weight reductions compared to a direct spring valve, primarily because as a pilot valve increases in size, the main valve increases, but the pilot is exactly the same all the way from a 1x2 through an 8x10. Whereas on a direct spring valve, as the main valve increases, the bonnet increases in size, the spring increases in size as well. And so that gets pretty significant in terms of size and weight, especially as you get into the larger sizes. Now, I visited a customer one time where I did a presentation on relief valve installations, and I did kind of what not to do. And I explained to that customer that you'd never want to install a direct spring valve in a upside down or sideways or diagonal installation. You always want it to be installed vertically and upright. A, to make sure you don't have any alignment issues with the internals, so the valve will always reclose, and B, to make sure you're still able to flow that full rated capacity. It's very important that it's installed vertically. Well, the customer took me to go look at some installations that they had where they had actually installed some direct spring valves in a 45-degree diagonal angle. And the reason they did that is because they had a height restriction where the valve was installed, and they just didn't have room to install it vertically. Well, we were actually able to replace those direct spring valves with a pilot valve because the height of the pilot was much less than the height of the direct spring valve. And they were able to, A, get all of the benefits of a pilot valve, but B, they were able to install it vertically upright in the way that it should be installed, and their plant is now safer today because of it. And so really, there's lots of applications out there where a pilot valve can solve customer problems. These are just a few of them that I shared with you today, but it has real dollars and cents in terms of savings for a customer. If you can find those and quantify them, I think you can be very successful at selling the Consolidated 2900. And so with that, I just want to leave you with a little bit of logistical information. And so first is I want to point you, if you've not been there, we've got a relatively new website for Consolidated, Mason, Elin, Becker, and Mooney at valves.bhge.com. And specifically, I want to point you to the Resource Center, which can be found right here at the top. There's a new section called Articles and Case Studies. And so as a product line team, we're going to be doing 10 sessions over the summer where we're going to cover various different case studies like the one I'm sharing with you today. And as we complete those case studies, we're going to be making them available for you here at the Resource Center. And so you can go get the case study we covered today in a one-page PDF kind of flyer format, all the same content that I just shared with you, just in a different format in a presentation. You can print that out, send it to customers, however you like to do that. That's all available there. And then I also wanted to show you there is a new section in Channel Connect. So if you'll come to Channel Connect and you'll come to the Consolidated Aftermarket folder, there is a new folder down at the very bottom. It's called the 2900 Pilot Valve Conversion Kit Program. And there's some useful information in here for you. So there is a 2900 conversion frequently asked questions document that will address some of your commercial questions, some of your logistic questions, technical, all that good stuff. There's a presentation that will explain the 2900 conversion kits, talk about the part numbers, the scope, the pricing, some of the marketing material that's been released and will continue to be released to support this initiative. And then there's what's called the 2900 conversion tool. And I'll quickly demo that for you here. And so in this tool, page 1, you're going to see some instructions. If you'll double click this page, it'll open up a quick little PowerPoint that shows you how to use the tool. But it's pretty intuitive. So if you'll just click on the Get Started, what you'll do is you will make your selections for the valve you want down here below. I'm going to do just a quick config just for the sake of this presentation. But you can see you're going to enter in the, excuse me, the set pressure. And the pilot type. Here, I'll just change this one to modulating just to give you an idea. Pressure class, materials, soft goods. Let's say I wanted something besides Viton. Let's say I wanted EPR, for example. Pick whatever you like. You're going to click Next at the top. Here you're going to select any options and accessories that you would want to add. Say you wanted to add a manual blowdown valve, or let's say you're not really familiar with the manual blowdown valve, or if you would need it. Down in each corner of the accessories, I've got some little help icons that will explain to you what that accessory is and why you may need it or want it. Here's a backflow preventer, inline filters, etc. So you can just say, yes, I want to add a manual blowdown valve. And then at the end, the tool will spit out for you all of the applicable part numbers based on the configuration you selected. So I picked a pretty complicated one just to show you how it works, but I'll get a 2900 conversion kit, plus I need to add a pilot SKU, a pilot spring, and it'll pick you the right spring based on the set pressure that you entered on the first page. I'll need to add a modulator because I wanted a modulating pilot. Here it's giving me a seal kit since I selected EPR instead of the standard Viton, and you get the idea. And so this tool is intended to make it really quick and easy for you to, after you convince the customer, hey, you've got a direct spring valve in an application that could be better with a pilot valve, you want to be able to say, oh, and by the way, I've got all the part numbers that we need to convert this 1900 to a 2900. Hopefully or ideally you have the conversion kits and the pilot SKUs on the shelf, and you can just convert that valve real quick and easy for them. So it's just as important to convince them and portray the benefits of the 2900 as it is to be easy to do business with. And so it's really a priority of ours that we make it easy for you to sell. So this is one of the tools to help you with that. So with that, I'm going to conclude the presentation. I hope you found this helpful. And I'm certainly looking forward to the other 9 sessions that'll be coming out this summer. So be looking for those calendar invites, and I encourage you to participate in those as well. So thank you very much for your time. And if you have any comments or suggestions or questions on any of the material that was presented or other ideas for case studies in the future, we would love to get that feedback from you. So thank you very much.